Attention functions as a biological mechanism for resource allocation, constantly filtering out irrelevant internal and external stimuli to protect our mental focus. One of its primary functions is search, the active scanning of a dense environment to locate a specific target embedded among distractors. Finding that target does not rely on simply looking harder. It depends on specific, quantifiable cognitive algorithms. Depending entirely on the physical data presented to it, the brain shifts between rapid, broad processing and slow, narrow processing. A highly structured computational triage system governs the act of seeing. Consider a baseline scenario, searching for a target that possesses a single, entirely unique physical attribute. In this feature search panel, the target with a distinct color pops out to the viewer instantly, without conscious effort. This experience changes when the target, in this case a panda, shares multiple physical features like color and shape with the surrounding noise. This shared feature environment forces the brain out of its automatic detection mode and into a resource-heavy, exhausting state. Why does the brain instantly perceive certain anomalies across a wide field, yet require exhaustive, linear effort to detect others? Anne Treisman's feature integration theory provides the framework that explains this discrepancy in search times. Treisman defines a feature search as looking for a single distinct attribute, such as a specific color, shape, or orientation. The brain processes these single features in parallel, scanning the entire visual field simultaneously. This parallel scan is pre-attentive, occurring automatically before conscious thought even registers the visual information. Because the process is pre-attentive, it requires almost zero active cognitive load. Look at panel B. The distinct curved feature of the O isolates itself immediately from the field of uniform distractors. Feature searches scale perfectly. Adding more uniform distractors to the environment does not increase the time it takes to find the target. The pre-attentive system breaks down when we encounter a conjunction search. A conjunction target is one identified by a specific combination of features, such as shape and color. Parallel processing fails here because the pre-attentive system lacks the capacity to bind multiple features together. This binding problem forces the brain into active, attentive processing. Active processing relies on a serial scan, requiring slow, item-by-item evaluation. In this panel, the shared features of the letters P, D, B, and Q create a serial bottleneck. Because these characters share the same line and curve orientations, the brain must deploy a sequential spotlight of attention to verify the target. In conjunction searches, cognitive load and reaction time increase linearly with every new distractor added to the field. The varying degrees of friction in visual searches can be explained by similarity theory. The core rule of the very states that cognitive friction increases proportionately with the physical similarity between the target and the distractors. This array of owls shows high physical similarity in both color and shape between the target and the background noise. Highly similar distractors actively divert limited attentional resources away from the target. This constant diversion results in processing errors and higher rates of false alarms. Commercial designers weaponize this effect, using identical color palettes and shapes to hijack your visual search in a grocery aisle. Carefully designed physical similarity actively degrades the brain's processing efficiency. Guided search theory resolves the rigid boundary between parallel and serial processing. The brain synthesizes both stages to optimize finite resources. Look at panel H. We are searching for a black circle within a grid of white circles and black squares. In the parallel stage, the pre-attentive system scans the field to create an instantaneous activation map for the first feature, the color black. Simultaneously, it creates a second parallel map for the secondary feature, the circular shape. The conscious attentive process takes over, but doesn't search randomly. The serial spotlight is guided strictly to the nodes where the parallel activation maps overlap. Guided search turns what could be an impossible scan into a highly targeted probabilistic evaluation. This algorithmic process is what allows you to find a specific friend's car in a crowded pickup zone. The brain immediately initiates the parallel stage, flagging broad features like white cars and tinted windows. The resource-heavy serial stage is then deployed only to evaluate vehicles where those specific features intersect. All other cars are dismissed pre-attentively, saving vast amounts of cognitive energy. Our unified, seamless visual experience is actually supported by an invisible triage system that is constantly running in the background. Visual search is a bounded system, strictly constrained by cognitive capacity. We operate between the instantaneous power of feature pop-out and the exhausting reality of conjunction fatigue. Understanding these algorithmic thresholds is critical for modern design, data visualization, and engineering. Any system relying on human vigilance, from medical diagnostics to air traffic control, must be built to accommodate these biological limits. In an increasingly cluttered world, understanding exactly how we notice is the only way to ensure we do not miss the signal in the noise.